Let's draw two different carbon atoms to see what isotopes are. If you look at the element square for carbon, you'll see a 6 here. That is the atomic number. The atomic number is the number of protons. Carbon is always the sixth element. It is, by definition, carbon because it has 6 protons in the nucleus. If you don't see a 6 here, it can't be carbon. For example, the atomic number for nitrogen is 7. That means every nitrogen atom in the entire universe, no matter what, has 7 protons in the nucleus. So let's draw a carbon atom. 1, 2, 3, 4, 5, 6 protons in that nucleus. And let's duplicate that over here because it's still carbon. 1, 2, 3, 4, 5, 6. Now, protons have a positive charge. Electrons have a negative charge, but they're not in the nucleus. We're going to make both of these carbon atoms neutral, which means that the number of protons and the number of electrons are going to be equal. The opposite of positive charges is the negative charges. So currently we have a positive 6 charge for each carbon atom. But if we want to make this neutral, how most atoms are just floating around in life, then we are going to have to add 6 electrons to each. So if we want to add 6 electrons, we're going to put 2 on the first energy level, and then the remaining 4 on the second energy level. The first energy level can only hold 2, but that's a different topic. Same thing on this side, 1, 2, 3, 4, 5, 6. Currently, both of these are neutral. We have 6 positives and 6 negatives for each one. They're basically just duplicates right now. However, something is going to make them different. Neutrons, although they have no charge, they have about the same mass as a proton. So if we want to make these two things different and not change the charge or which element they are, that's where neutrons come in. Neutrons have mass, so if we're going to add 1, 2, 3, 4, 5, 6 neutrons to the one on the left, and 1, 2, 3, 4, 5, 6, 7 neutrons to the one on the right, we've got to update our inventory. So 6 protons on each, because they're both carbon, 6 electrons on each, both of them are neutral, and protons equals electrons in terms of number when something is neutral. However, the carbon atom on the left has 6 neutrons, while the one on the right has 7 neutrons. That makes the one on the left a carbon-12 atom, and the one on the right a carbon-13 atom. Where is this 12 and 13 coming from? If you sum up the number of protons and neutrons, which are the things in the nucleus, collectively we can call protons and neutrons nucleons because they're in the nucleus, then we get 12 on the left, and 6 plus 7, that's 13 on the right. This 12 here and that 13, those are called the mass number. So the mass number of the carbon-12 isotope is 12, protons plus neutrons. The mass number of the carbon-13 isotope is 13, protons plus neutrons. So what's different about these two things? They have different masses or different mass numbers. So let's write the approximate relative mass for each one. Relative mass. For proton, it has a relative mass of 1. For electrons, it has a relative mass of basically 0. It takes a lot of electrons to equal the weight of a single proton or neutron. And then a neutron has about the same mass as a proton. So when we talk about the mass number, that's why we only consider protons and neutrons, which collectively are called nucleons. So what is the connection between the carbon-12 and the carbon-13? Both of these are called isotopes. They are isotopes of each other. So both of these are considered carbon isotopes. What makes an isotope different from another isotope of the same element? It has different number of neutrons. And that's key. It's not the number of protons, it's not the number of electrons, it's the number of neutrons between the same element type that makes them isotopes. Something to note about how we can denote isotopes, we can do it this way where we write out the name dash the mass number, so name dash mass number of the element, but we could also just write the symbol, which would be C-12 here and C-13 over here, so symbol dash mass number. And another way you'll commonly see it is the symbol with the mass number at the top, so C and then a superscript 12 to the upper left, so here it'd be C with a superscript 13 on the upper left. Now sometimes even, you'll see the atomic number added as well in the lower left. That's optional, but for carbon it has to be 6. So a 12 over a 6 with the C, that's just another way to write the element or the isotope symbol. 13 over a 6 with the C is another way to write it. So this is one way to write it. which is the same as saying this and the same as saying this. It's worth noting too that there are other isotopes of carbon. So there's another carbon isotope that's naturally occurring called carbon-14. And as you could guess, carbon-14 has yet another neutron compared to carbon-13. So it'd be 668. Remember, the number of neutrons plus the number of protons is the mass number. So carbon-14 has one higher thing in the nucleus, and that extra thing is a neutron. So what is this number here? Notice how 12 and 13, which are the two most common carbon isotopes in the world, they are on opposite ends of this number. So 12.01 is much closer to carbon-12's number than carbon-13's number. That number there, the average atomic mass. The average atomic mass tells us the relative ratio of which carbon isotope, or which isotope at all, but in this case carbon isotopes, are abundant in the world. So because this number, 12.01, is closer to carbon-12's number than carbon-13's number, there are many, many, many more carbon-12 atoms than carbon-13 atoms in the world. So the average atomic mass is just a weighted average. Now let's fill out this diagram. You will need the periodic table to understand how this works. But it's kind of like a puzzle. If you've ever played something like Sudoku or whatever, we have to use logic to understand it. This 13 over C is just another way to write carbon-13. Now, nothing else is even over here, but if you look at the periodic table, you'll know that the atomic number for carbon is 6, which means it has to have 6 protons. The immediate pattern you are going to have to recognize is the number of protons is going to always be equal to the atomic number. What about the number of neutrons? Common mistake is that people look at this mass number here, which is 13 in this example, and they'll think it's 13 neutrons, but that's not true. Remember that the mass number, this 13, is the sum of protons and neutrons. So let's skip that for now and come back to it because we know immediately that the mass number is 13. It says it right here. But the mass number is the sum of protons and neutrons, so 6 plus what equals 13? The answer is 7. So remember, mass number is protons plus neutrons. Number of electrons. We're going to assume that all of these are neutral elements, so they haven't lost or gained electrons, which would change the charge. So the number of electrons will equal the number of protons, and that's going to be 6. So all of these are neutral. Now, this is interesting here because we don't know what isotope it is. We only know the atomic number and the number of neutrons. Immediately, you're probably thinking, well, if the atomic number is 17, isn't the number of protons 17? That's correct. And since you know the atomic number, which is the number of protons, you could go to the periodic table and you could go to the 17th element and you're like, okay, that's chlorine. Which means you can put a big Cl here. 17 plus 18, so 17 plus 18, that's going to give us the mass number, which is going to be 35. That means that this is a chlorine-35 isotope. And since we assume it's neutral, it's still going to be 17. So you can kind of go down this list if you get something like this in class and immediately just add or make sure that the atomic number and number of protons are the same. So 26, 26, 17, 17, 52, 52, and 50, 50, because again, these two are equal. Looks like we have another chlorine. So let's put Cl here, and let's see what's actually different about it. This is interesting if you notice that the mass numbers for these two different chlorines are different. One of these is a chlorine-35, and the other one we see is a chlorine-37, which means it's a different isotope of chlorine. What makes that chlorine-37, which is this one, what makes chlorine-37 different from chlorine-35? It's the number of neutrons. So we have 17 is the number of protons, 18 neutrons here, but since this is a 2 higher mass number, there's got to be 2 more things, and it can't be 2 more protons. It's got to be 2 more neutrons, which means that the number of neutrons here is going to be 20. And if you notice, 17 plus 20 is 37. What about the number of electrons? We assume that it is neutral. So since all of these are neutral, we can also make these numbers the same. Now we can also go ahead and put the symbol for the third row. So atomic number 26. If we go over here, we see that 26 is iron. So we can put Fe. We already see that the mass number is 56, so you can put a little 56 right there. And the number of neutrons, if you ever have to figure out the number of neutrons, all you got to do, I'm going to put it here, number of neutrons is equal to the mass number, subtract the atomic number, or the number of protons. So For the iron one, it's 56 minus 26. That means that there are 30 neutrons in that isotope of iron. This one has two numbers, a 2 and a 3. So we have 2 neutrons, and the mass number is 3. Since the mass number is number of neutrons plus protons, 3 minus 2 is 1, which means that there's just one proton in that thing. If there's one proton, then the atomic number is 1, and that would give this, or make this, a hydrogen isotope, or atom. Which isotope is it? Hydrogen 3. How many electrons? If we assume it's neutral, 1 proton, 1 electron. This is a large one, has a large mass, so 128. Now, since the number of protons is 52, which means the atomic number is 52, we're going to go to the periodic table and we're going to find where 52 is. 52 is tellurium, so it's Te. So we can put Te, and we see that the mass number is clearly 128. What is the number of neutrons? The number of neutrons is the mass number, so 128, minus the atomic number, which is 52. That's going to be 76. So there are 76 neutrons in that isotope of tellurium. And then lastly, we are looking for the 50th element because we're looking at 50 protons, which is the atomic number 50. So we're going to find number 50 on the periodic table. That's going to be 10, which has the symbol of SN, weirdly. And since we know that the mass number is protons plus neutrons, that's 50 plus 70, which is 120. So this 10 isotope has a mass number of 120. And that's how you would fill out one of these diagrams if you were asked to do so in class. And hopefully that helps you understand mass number, atomic number, and the relationship between the subatomic particles.